Uh, as I explained last week, we will start with the chapter 5. Again, at the very beginning, I explained this whole class of solid mechanics has a two part. One is the solid 1 and 2. And since our class is solid mechanics 2, we will start with the chapter 5. So chapter 5 is about stress and strain transformations. Well, the concept of stress and strain are the very essential for whole class. And chapter 5, we have several sections. First, we like to introduce the stress, and the second, Mohr circle. We will learn about the Mohr circle, and together with the symmetry of a stress tensor, and the observations of a Mohr circle, and then we will also learn about the introduction to strain. It's basically stress and strain themselves. Now, let's define the stress. So, what are these stresses? Okay, let's say we have a certain object, and this object can be subject to an external force. Let's say a lot of a force outside. These outer forces will be or have to be in equilibrium. But anyhow, let's imagine that we a body, and then a lot of a load applied to outside in general. Now the point is that what will happen to inside? Any point actually, but let's pick that one arbitrary point, and then we call O. So to see the stress inside or defined at a point O, we like to cut it out, just cut, and then try to see what's happening on that surface. Once we cut, then we will have a certain forces that will be two forces basically. Let's say this is pretty much conceptual at this point, but again, if we cut this body through that O, and with the direction of a certain the plane of directions, and then this Fn, I would say this is n, and this is the t. Okay, this is a kind of vector which represent the surface. Now, the important concept is the surface. Surface also represented by a vector. What do we mean by the vector? It means that it has a certain directions. So again, let me say again. Let's say to take a look at inside the stress O, we first like to define the normal vector n, which has a certain direction. and then plane, the way we cut is that this n is the normal, represent this surface, and then the surface, and this n is the always a normal. So again, the surface is represented by the normal vector. Okay, this is the so once we have a cut, and there will be a certain force, we call Fn. Why do we call Fn? Because the this is a n, and there will be a distribute. Actually, this is not the point force. There can be sort of a distribute force like that, but we just like to focus on one point, O, and let's say there's a force distribute over the force, and we represent the Fn. Now, this Fn is also a vector. So we specifying two vectors. One is this n vector, and the other one is this force vector. Those are two vectors. Those are key points. And this normal vector, distributed vector Fn can be decomposed into a normal term and then tangential term like this. And this normal term we call n component of Fn n component of Fn, and tangential term is the t component, okay, t component of Fn. It's a little bit of a mistake, but anyhow, point is that we have a two component of a force. So this normal term we call sigma nn, and this tangential term we call sigma tn. Well, I like to read here. When an object is subject to an external load, there are also loads induced inside the object, right? The directions and magnitude of such internal load depends on equilibrium conditions and material property and deformation and comparability condition. What does it mean is that the stress which will occur at a point O will depend on the material properties and all kinds of physics. We don't worry about that, how these stresses are distributed. We just like to define that. To express the internal load at an arbitrary point inside the object, we first need to determine the normal directions passing through the point. This is the very important point. Normal direction of the plane, and then determine the directions and magnitude of a load, determine the direction of the magnitude of a load distribution on that plane. So as you can see that we need to define the two vector. One is the normal vector, and there will be a force vector. And then the force vector will have a component in the normal term and shear term. That's why we call sigma nn, and this one is a sigma tn. Well, it could be a little bit confusing, but let's move to next one. So stress, this is just a plain two-dimensional case. This is just a repeat of what we just defined. There's O, and we have a n vector. Why n vector? Because we want to cut. We can cut here, many directions, but we like to have a certain plane, and then the area plane, which is always represented by the normal vector. Okay, so cross section is also a vector. So n vector, we have a crossing plane, and then we can say there is a certain area, and tangential we call t. So t and n is always a normal. Now, once we have this plane, we observed a certain force. This is we call Fn. Why? Because this area is represented by n, so we call them Fn. Now, this Fn needs to be, or we like to decompose into normal vector and then a shear vector. What I mean by normal is always a vertical toward this plane, and then tangential is a shear. So we can have a decompose. We can decompose this vector. So that's why we call sigma nn and sigma t. This is exactly what we explained the previous slide. So Fn has two components. First, this is the unit vector normal to the plane and tangential vector. And then first we'll have a component. So we can see that we have a normal vector and we have a force vector. And then each direction will have a component. That's why we now need to define the sigma nn and sigma tn. Now, I mean, we already know much about the force or vector, but this stress is the higher order than vector. Okay, let me get back to that point again, but let's keep on. There could be another vector, another area. Let's say there is O, and now let's say we cross this point with now with the t vector, which was defined previously. So this now is a t vector and n vector. As you can see that t vector and n vector is has a 90 degree, and then we will have a certain vector distribute on that point on this area. On area, what I mean on this area is the area represented by t. Now this ft will have a component in the t direction and also shear directions. So that's why we can call this is a sigma tt, and this is a sigma, but this is not right. Well, sorry. This is a sigma nt. So we have a two component, sigma tt and sigma nt. Okay, of course we can have a totally different directions, like this, or like that, and like that. And then the story can go very similar to what we have done here. N vector, t vector, and then a component. So again, n vector, t vector is arbitrary. So n vector can be and t, but the point is that n vector and t vector is they are perpendicular to each other. So we have a body and we have a O, and what is going on here? How do we define internal forces? Internal force. There should be or there will be something goes on because of this all external force, and to represent what's going on is that now this can be represented by this 2 by 2. One is the sigma nn and sigma n10 tn. That was like this, and then we had this and that, right? And then another one is that t vector, we just have another cross section which is perpendicular to this t. We have a tt and sigma nt. Okay, this is the definition of the internal forces in a body. This is the n vector, and this is a t vector. Okay, so the stress into mutually perpendicular plane passing through, this can be important, passing through an arbitrary point O can be expressed by normal and shear component each plane. Okay, this is a normal and shear. This is a normal and shear. So we just arrange them. You can see that there's a Tn and there is a Nt. Nn is clear. So I would say pay attention to here. N. Now you can see that always we need a 2 index. First one, n vector, representing cross section, and this n is represent a vector which of the force which occur in the plane on the surface, and here sigma tt, same t plane and t direction, and n plane and t direction, and t plane and n direction. So that's why this is just I would say definitions. We do understand there are 4 components, and then we represent those 4 components using 2 by 2 matrix. Matrix is now convenient, very convenient to represent those 4 components. Okay, let's move on. Now let's take a look at the 3-dimensional. But before go to a 3-dimensional, you may wonder, okay, we can cut this one, but the t, this is n, and you may wonder, how about we can cut here, like t, we can cut any plane. So n and t, but the one point is that n and t, they have to be perpendicular. Why? It is a concept like this. Let's say we apply the force here. How do we represent this force? Well, without any hesitation, you say this is x and y, and then you can say this is fx and fy. Now you can understand this way why we have a xy, they are perpendicular. This is a Cartesian coordinate. To represent this force F, we define the Cartesian coordinate, perpendicular coordinate, and then we have a decompose. So fx and fy. This is a very the the conventional way of defining vector, right? So again, as you can see that now we go through two times of vector definitions. First one is that here we have a one vector, the cross section. This is represented by the normal vector. Of course, this will normal vector, and then there will be some force which will have a certain component like that. But now you can choose any perpendicular like this. In other words, let's say this is very important. F, can we define the other coordinate like the like this? I will just say x prime and y prime. Of course we can. If we define the x prime like that and y prime like that, then this f will have can be represented by this way. This one and that one. So this one will call fx prime, and this will call fy prime. So same f can be represented by the fx and fy, which is the same as the fx prime and fy prime. This is a very simple but very important concept to extend it to 2 by 2. We don't have I hope that we don't have any problem to understand the force in a certain direction and another direction. So again, here, internal force, this is a force vector, represented as just a force vector. But representing internal forces, just a force is not enough. Okay, just a force is not enough. What else do we need? Well, we need a cross section and see the force. So cross section represented by one vector, and then another vector we decompose. So that's why we have this is I would say n. This is a t, and this is n and t. So I'm just repeating because this is the first concept. First is very important and first topic to you. So I'm just repeating. Now let's say extended to a 3D body. Now this is a three-dimensional rather than just a 2D plane. Let's say we have a O, we have a vector n and t, and another n vector. So to take a look at this, what's going on here, internal force, the procedure will be exactly same as a two-dimensional. So first we have cross sections. We like to have a cross sections like this, and then which is represented by the t. And another plane will be t. We just cut here, plane like this, and then this is represented by the t. And another perpendicular plane is the m, like this, and this is m. Now, the concept is same as a 2D, but as you can see that m vector, t vector, another m vector, we can have a three vector. Importantly, they have to be perpendicular to each other. Very similar to our conventional definition of a Cartesian coordinate, x, y, z. They are always perpendicular. And then you can rotate, say, n vector. Say you can rotate. This is n vector and t vector. and this is an M vector. So you can freely rotate. Imagine you have 3 fingers. You can freely rotate. Okay, and now obviously each plane we will have another distribute. Okay, distribute the forces. Okay, distribute forces. You can call them Fn. Now this Fn could have a component, 3 component in a direction of n, direction of t, and direction of m. That's why each component we call sigma nn, tn, and mn. And same to the t, we can have some distribute ft. Now we can it can have a component sigma n, nt, tt, nt, and mt. So this is the component like this. And m, the same. We will have a fm, and fm will have a component in a direction of mm, normal, and tangential, t, and n. And one thing we like to notice is that this surface, any surface, this surface, any surface, we always have one perpendicular plane, a perpendicular direction, and we always have 2 tangential directions. That's the definition of a plane, one perpendicular and always 2 tangential plane. So anyhow, we represent this 333. We just list them here. Okay, we like to list them here. This is the, I will say 3 component here, and then another 3 component here, and another 3 component here. But we intentionally have a certain direction. This is the normal, NN, TT, and MM. I know it's confusing. This is a TN, this is a NT. And MM, NM, and MM is which goes here, which goes there. Even I didn't pay much attention here, but let me explain later why we don't have to pay much attention. The point is that this is the one vector, the vector on the n, and t and m, and this diagonal term. This is a diagonal term, right? This diagonal term always represents a normal component. And this one is a shear component. Okay, let's move on. Okay. Now I'd like to observe the symmetry of a stress tensor. Now we call it stress tensor. Why do we call tensor rather than vector? Vector has the one component, one directions like that, but the tensor means that we need to have a 2 component of a vector. That's why we call them tensor. Actually, the vector is also one of a tensor, but for at this point we just call them a tensor. Okay. And then what is the symmetry of a stress tensor? Okay, back to the 2-dimensional case. we can cut here and we can cut here. I mean, previously we can cut here, but these two planes can be arbitrary. We just cut x and y. Now, to represent the point here, it is convenient to define a small rectangular like this. And then here we just say normal and shear, and here is the this means this one here, and this one, and then shear, and this opposite direction. I mean, if we when we cut it, we can say here, but we can also see this object as well. So this plane, we can see this one. So anyhow, we can define a rectangular, and this is a rectangular. And as we just defined, this will be the sigma xx and sigma yx. And the in the opposite direction, because of uniform stresses, uniform stresses, there should be a sigma xx, and this is a sigma xx, and this is a sigma yx, and yy, and yy, and xy, and xy. Okay, a little bit confusing, but this is something like that. When you have a fx, you would need always the fx in the opposite direction. This will be the same, right? So this is the equilibrium. If I cut here, then what will have? This will have like this. So this will be the fx as well. So no matter where you cut, the force will be always the fx. Now, if we look at the left-hand side, this is the fx, and the this surface will always have a fx as well. So this point, when we cut here, we can see this is fx, or we can cut here. If we look at the right-hand side, there will be a fx. So of course, this fx and fx is very similar to concept of action reaction. Action reaction. So rather than just the one point, we just define a small rectangular, and then here we represent this, and this, and this, and that. And also, as we notice, that there will be some shear stress and things like that. Now, the point, the subject we like to study is the symmetry of the stress. What does it mean? Symmetry of the stress. Okay, this rectangular, I would say this is a very small length, if dy. This is a small length, dy, I mean dx. Then let's take a look at the stress. Now, not the normal, only the shear stress. We had a shear sum here, and the shear here, and the shear here, and shear here. You may wonder why just an objection? Because we have a coordinate like this. So here, the positive direction is y. This is a positive direction, and this is the x, but the positive x is like this. this is the plus x direction and plus y direction, and this is the minus x direction, and this is the minus y direction. So we have this negative direction like this. Okay. Now, if we look at these two components, this is the action reaction, very similar to the action like this and like this. I mean, normal stress, we feel okay, very easy to imagine. But shear stress is a little bit is confusing. This is natural. Okay, don't worry. So this one on the top surface we have this one, but as like this positive direction, negative direction, we have a opposite forces. Very similar to that, we have a opposite. And also this plane, we have a positive, and this is a negative direction, we have a negative. Now, this guy, this body, actually, we have one body. Similar to the concept, like this is the sigma xx, sigma xx, these have to be same. Why? These force have to be same. Very similar to that concept. Now this one, we have of course, this will be a force, there will be a force equilibrium. This one and that is a y directional force, there will be equilibrium. And this is a x direction equilibrium. But there is one more thing, is that rotations. Why do we consider rotation? Because these two forces may cause a rotation, twisting. And these two forces, even though they are in force equilibrium, they may cause a rotation. So to have this body in rotational equilibrium, we have to have a moment equilibrium. Moment is the sigma xx and sigma xx. And the this time, to make the force, this is a distributed force, we have to apply the cross section. And this is also cross sections. That's why the sigma xy, sigma xy multiplied by dx, this times d gives us a force, and then a distance dy. You know, there is a, you know, the couple. Okay, this is a f and f, and this is a distance d. Then this gives us a couple or a rotational moment, f times d, right? F times d. So F is a force. To get the force, we have to multiply this distribution times cross-section area. This is important. So the first sigma xy and the distance, I mean the area, and then distance gives us what is this? This is a minus directional twisting moment, and this is the plus moment like this, and then this have to be 0. So dy dx, dx dy will disappear, and simply we will have this. Sigma xy has to be always the same as a sigma xy. Even though we consider a 3D body, this one is just simply like this, and simply like that, and then this, and then, so we just notice this one. But in the 3D, same thing. We have this and that, and this and that. They are always the same, this and that. and then something like that. So we just observe that sigma xy and sigma yx, they always the same. That's why I didn't pay much attention. Is it xy or yx? Why? Because they already, they have to be same always. Just for the because of a rotational force moment equilibrium. And this one and that, they have to be same. And this one and this, they have to be same. So in symbolically, we can say sigma ij equals sigma ji. So I can be x, y, j. J can be also x, y, j. So this 1, 2, 3 condition can be represented by like this. Very same. So the sigma, very important point. Okay, sigma ij equals sigma ji. This is because of a moment equilibrium. Very important concept. Symmetry of stress. So we had an 3 by 3, 9 components, but now independent component is the only 6. 1, 2, 3, 4, 5, 6, because these are all symmetry. So 3 by 3 gives us 9, but the independent is the only 3. 3 normal and 3 here. Okay, this here is the same. So that is the condition of the shear stress. I mean, the symmetry of the shear stress. If anybody has the first time you learn about this stress, I'm sure it is confusing. But don't worry too much, because a new concept, to understand new concept, it may take a little time. But you have to keep thinking. I mean, vector is easy, but the twice over vector is the stress. And first vector is the cross-section vector, and second is the force vector. And then those shear term is the always symmetry. And that is, this 9 component will represent a distributed load in the body. Okay, now this is the very important is second steps. Now what we like to do next is that here now get back to 2 dimensions is a rather simpler. Here we have a stress like this. Now here the same point, okay, this is the point, same point but different axis. See, xy is here, okay, xy is here, but now we have a kind of a inclined surface, inclined coordinate, which is say rotation by the theta from xy. And then from x prime, y prime, you can define the stress in like this. Another component, 1, 2, 3, 4. And this is a 1, 2, 3, 4. But the very important point is that this sigma and this sigma they are same. This is exactly like this. We have a f vector, okay? This is a f vector. This f vector can be represented by this xy with these 2 components, right? Now this is the same f, okay, exactly same f, But now we have a different coordinate system. This is X and Y, which I already explained. This is X prime and Y prime. Now this is F, this F and this F, they are the same. And now X prime, Y prime, we have a new component like this, and this is X1. So again, this is, you can say Fx and Fy. And this one, you can say Fx prime and Y prime, Y prime. And again, these are same. Here, the X prime and X, there are angle theta. The same here. This XY and X prime Y, we have angle theta. Now, I'm trying to get back to vector because you already know. Fx prime, you know how to calculate Fx cosine theta plus Fy sine theta. You know, this guy, Fx prime, can be represented by these two components with the theta. This theta is the angle between two axes, x and x prime. And also fx prime can be fy cosine theta, and fy is the sine theta. And one of them is the minus here, right? This is the one we learned long time ago, even in high school, and this is called what? Vector transformation. But do not just remember that. The concept is that this f is the same, but two different coordinates. We have a component, fx, fy, or fx prime and fy prime. So this is the how we calculate. Very much the same. Here we have a sigma. Now it's no longer vector. We have a matrix, 4 components. And same here, we have a stress, same stress, okay, same stress, but different coordinate system. Now here the definition of a coordinate is the cutting plane. We can have 4 different components. Now, very similar to here, this guy should be represented by this component with a theta, a function of theta. See, you can see that this is a theta and theta. And the same for this. So this component represented by this, given in terms of this, and this one same, this one will be the same. But this will be the same. So we only need only 3 equations, this one, and that, and this. So keep that in mind. This is a what do we call? Vector transformation. Actually, we don't transform means that rotating, but this is not the rotation. It's just a transform means that from a certain space to a certain space, or a certain coordinate to another coordinate. So that's why we call transformation. And this again the core concept. So what we're gonna do, what we like to do is that we like to drive equation similar to this. So normal and shear stress in inclined section. Inclined section means that in vector, we have another coordinate system. We like to get the component in terms of a previous another coordinate system. So a little bit complicated procedures, okay? And we like we had this rectangular which represent an x and y, and we already know this is a stress here and stress here, normal, and also shear and shear and shear. This is the way we represent the internal force. And now to get the relation similar to this, how do we get this? Well, we defined a inclined surface, which is now x prime. So normal component will be a sigma x prime, and this one is x y prime and x prime. Again, you can call it x prime y prime. So don't worry. Now here is the already have a 4 component and 4 component. To drive the relations, we have to consider equilibrium condition of this triangle. We have this much force and this much force. No matter what they have, what we have here, this triangle have to be in equilibrium, and that's the way we drive these terms in terms of this. So, okay, equilibrium. Equilibrium is the key. Equilibrium. We will obtain. We will use the equilibrium. Sigma f x prime. What is x prime? X prime is a direction like this. So we have this force on this incline. How do we get this one? Now, very importantly, to get the force, we always have to multiply the cross sections because this is a distributed load. So that's why sigma x prime times L. Now we define this one as the L. And there are another x prime force. Well, this is not the x prime force, but this guy will have a component of this one and this one, right? And this guy also have a component, this one and this one. And this one also component of the this direction and that direction. So this one also have a this component and that component. A little bit complicated, but conceptually, conceptually is not that complicated. We just take the x prime force. Okay, this one, and also x prime. Okay, I will represent different color. This one, okay, this guy, this one, and this guy, this one, and this guy, this one, and that one. That's why the you have a sigma xx. See sigma xx. Where is the sigma xx? Sigma xx, for example, like this. Sigma xx times ly. This is the let's call ly and lx. Now sigma x, this one, to get the force, we need to multiply ly. So sigma xx times ly will give us the force. Force means this one, and then we have this component with a certain set angle. That's why we have a sigma cosine theta, and then a minus traction. This is a minus traction. Okay, so the point is that if we have a L, we have a LX and LY, different cross sections, and then we have a force decompositions. So we do so 1, 2, 3, 4, and 1, 2, 3, 4. You can follow them, and very importantly, this LX, okay, LX will be is what L times sine theta. Ly is L times cosine theta. So we put these things into here, Ly here, and here, and then here. So as we notice that first time cosine is coming from the decomposition of a vector, and the other second times we have another cosine and sine theta. It's because of a cross section is the reduced. So that's why. Okay, these have to be 0. So Lx prime x prime on the left hand side, and this is all right hand side. You can see that we have a divide by L, then we can have a cosine square, sine square, and then this xy and this xy is the same. So this is a sine theta, and this will be cosine theta. And cosine theta and sine theta, we have a twice, so we have a twice. Okay. I mean, we don't have to go through a very detailed, but you will get the concept that sigma x prime, now sigma x prime, in terms of xx, yy, and sigma xy. And then a cosine square, sine square, and then cosine sine, and there is a twice. Okay, this is the conceptually same as this one. You don't need to remember all the equations, okay? You can, but the conception is that you have a decomposition similar to a vector, but instead of a cosine, instead of a sine, we have a twice of a cosine square, sine square, and cosine and sine. All of them are twice of a cosine sine. Why? Because first cosine or sine comes from the vector transformation, vector decomposition, and the other one is the cross section reduction. So this is the one we got this. A little complicated. I know it's a little complicated, but this is the really important equations which will govern what is going on and what kind of internal forces will happen on any plane. Here is the L and L cosine theta, and then L sine theta. This is the Ly and Lx. Now we can do the exactly same. Now in the different force equilibrium, we can consider y prime directional force this way. So this way means that we can have this component, right? Now we have this component and this component and this component and this component. So this component we need to multiply L. Now others, you have a sigma xx times the L. What does it mean? This is a force, and then a decomposition. Exactly same procedure as we have, and then Lx, Ly, we have a relation like that. Put it there, and then we divide by the all L out. Then we will have a sigma x prime y prime. This is the final equations. This is the sigma x prime, and this is x prime, y prime. Well, again, I know it's a complicated equation in terms of all the sine and cosine. You don't need to remember. But conceptually, you remember like this. Okay, same F. Now with a different coordinate system, each component will have a relations. How do they calculate from previous coordinate component. Exactly the same. And then there will be another similar one. We can now have instead of this triangle, we can consider this triangle as well. So now we can do exactly the same. Repeat what we learned. Y prime and this equilibrium means that we have this force and we have this force, and we have this force and this force. We get this. I'm sorry, the x prime, y prime, y prime. We get this, and then another equilibrium we have from this y prime direction, and then this is x prime, y prime. Okay, so how many equations we get? We get 4 equations. 1, 2, 3, 4. You may forget the procedures and final equation, but the concept is that the purpose is that there will be some internal forces which will be represented by the certain component of matrix. If we know the stress in this coordinate, how can we calculate the same stress but with a different coordinate? That's the point of the transformation. Same concept as the force transformation, and derivation is a little bit complicated. This is a final. Okay, this is the final equations. Okay, I will just quickly go through Excel. I'm trying to help you better understand, starting from the concept which you already know. This is the concept we already know. What we like to do is that we like to get this is the fx and fy are given. How these fx prime, y prime will vary according to the theta. This is what we like to do using the Excel. So imagine that say this will be the fx. Okay, this will be the fy. Now we have a lot of theta. Theta will vary from 0 degree to the say this one. Theta should be a radian, but we can say simply like this 5 degree. Okay, I will change it to a radian later. So you can see we like to have every 5 degree, and then oops. Let's say we change it to 180. Okay, 180 is the target. So imagine that we changing this angle theta from the 0 to 180. Now here, importantly, this is the fx prime, and this is a fy prime. This is a two component, and what will be the given? Fx will be the given, and then fy will be the given. So this one, I will say any value, and let's call this guy as fx. How to do that? This is Excel. You can using the define name. Because sorry. Oh. So define the name using create from selection. So automatically left column will give us the name. Means that if I say okay, then now instead of okay, what I like to do is that we like to change it to say radian. There should be some yes radian. Oops. Radians of this guy. So a copy and paste up to here and give up the all the angle in radian. As you can see, pi is the 1 point and 2 pi give us, this is a pi, 180 is a pi, so 3.14. Okay, this is nothing but the radian. And then I will call this guy as a create top row will, theta will be the name, okay. So now here is equal, just follow this one, fx, it just automatically show this one, times cosine and theta. What is the theta? We already defined as this one as the theta. And the plus fy times and the sine theta. Okay. So it automatically gives us some value. Let's, and then this one, very similar, but as you can see, there's a minus sign and plus cosine. So there is a minus, and instead of a cosine, this is a sine, and this will be cosine. Okay, so it just a bunch of a number, but let's try to plot. Then you will get a better idea. So Excel, you should know how to plot them, and using here and the using this vector. Okay, so this is the equation, but this is a just graph. X is a theta, and then a vertical axis is the either fx prime and fxy prime. Now you have a 10, 20. That's why you start from zero angle. You have a 10 and 20, right? Zero angle means should this guy, these two components should be the same as this one. And then as angle goes by, this component will change. And this is what the equation says. Now we just graph them. And now you can play with it. This is now Excel, it can be very powerful. You can just change that. Say you can just change the value, automatically change. If you change the some value, any values will be like this. Okay. Now, rather than just the plus, I like to 10 degree. So that we can have a whole 360. So rotating 360 degree, and this is the variations. As you can see, at the very beginning, you have a 0, 10, and 20, but the 360, you also back to the original value, right? This is the value, same value. And again, with this simple Excel, you can get the idea how these forces are changing. And very interestingly, if we have a 10 and 10, and if we have a 0, and okay, so this is a how variation. Now, next class, what I'm gonna do is that we like to do exactly same as here, but we like to calculate these stresses, how this changes. Here, see x prime, y prime, and this, and again, this is the x prime and x prime, y prime, and y prime, x. These are same. We don't need this one because we know already they are same. So you can plot. You can using this equation. You can do the exactly same, a little bit complicated, but it's quite doable, right? We can do that. Okay, I already have it. This is what we have here. This is the sigma x prime, y prime, and x prime, y prime. And then a cosine theta. And I just calculate the cosine and sine here. But as you can see, from angle to 0 to whatever angles, you will get the variation. And this is the curve. Okay, this is the curve. So this is the sigma x prime, and this is the y prime, and this is the x prime, y prime. As you can see that, how you can see it, very interesting. Now these three, you can specify the any value, 2, or you can say 2. See, this is very interesting. Depending on some value, they don't change it. Oh my God. This we cannot see from the vector, but the stress is very interesting. And this is the very easy way using the Excel to observe how the component vary. So, okay. So I will share this Excel with you. And this is what exactly like to learn from this class. It is called stressor transformation. Okay, so there is some definition of a Mohr circle, which is very important. But the more important concept is the how these stressors vary. Okay, I'm sorry, I need to close the class today. At this point, I will share this Excel file. Okay, sorry, not much time. If we have any question, feel free to ask in the cutoff. Okay, so I need to say bye. See you next week. Just hold it, hold it. Don't move. I need to have a class. Oops. Well, it's okay. Thank you, and sorry for the shortened class. I will assign the homework as usual, and then just try to think. You don't need to look at it again. Just try to think what you learn from this class. Just keep thinking. As I said, I will upload this whole class in the YouTube, and I will share with you. Thank you, and see you next week. Bye.